Well, thank you very much. Okay, and I thank you, the organizer, and you back there. Thank you very much for inviting me. Okay, I like this format of the conference. Okay, because sort of very relaxed, 2 talks in the afternoon, 2 in the morning. Okay, and lots of time for discussion. So in the same spirit, please interrupt me. Okay, anytime. And it's not important for me to finish. It's more important for me to get questions from you, okay? So let me give you an outline of my talk. So in my group, we do large-scale simulations, okay? And so these simulations are in the scale of petascale, 10 to the power 15 operations per second. And most of the simulations we do are on very large-scale machines provided to us by the Department of Energy. Okay, so we compute at national labs. And for our group itself also, we have a very good system. We have a 2500 CPU system just for our group. And then the university provides free computing also. So the computing situation is very good. So at the moment we are doing petascale, but in the US there is a big initiative to go to the next scale, which is ettascale. And so the new machine which is coming is 100 petaflops, 0.1 ettaflops. And we have just gotten access to that machine, okay, and hopefully we'll be looking at larger systems and longer simulations. So that's the first thing. I'll briefly describe to you what we do, okay, on petascale machines. The second topic is, I wanted to say something which is relevant to the theme of the conference. So I picked this one example on aluminum nitride, and I will show you, high strain deformation in this system and what is the nature of plasticity in fracture. The metamaterials, this is a new topic for us. Okay, we are very interested in it, and I'll tell you, these materials have very interesting properties, unusual mechanical properties, for example. Okay, and they can also have unusual optical properties. But we are focusing on mechanical metamaterials, and I will show you some simulations on high strain deformation in these materials. And the last topic is ceramic nanocomposites, and there have been some beautiful experiments done in Japan, okay, where they have looked at crack healing in ceramic composites. And so the simulations we have done is to see what is the mechanism of crack healing in these nanocomposites. Okay. So before I, go into the applications, let me say a few words about the simulation approaches we have. So at the very small level, at the level of electrons, we can do quantum simulations. And when I say quantum, not just density functional, but quantum dynamics also. So for example, if there are, excitation processes involving electrons, okay, jumping from one electron level to another, because of external perturbation, we can look at those processes. Now, experimentally, these processes become very relevant when you're doing experiments which are like pump probe experiments. So you're pumping the system, okay, at, let's say with lasers, and then you're probing them. And these days you can probe them with free electron X-ray laser. And in that case, you can probe the system experimentally on the time scales of femtoseconds to nanoseconds. And so those experiments are sort of very relevant to us because they can give us information on quantum dynamics. Okay, so that's one scale. The second thing we do, now this thing is limited to a few thousand atoms, okay, these fully quantum dynamic simulations. The largest simulation we have done in our group is 16,000 atoms, okay. Then we go to the next scale. We say, okay, let's take the input from quantum simulations. We would fold that into force fields, and these are reactive force fields. So for example, in the study of fracture and so on, bonds are breaking, and so you need force fields where when the local environment of an atom changes because of bond breaking or bond reformation, then you want the force field to capture that. And these force fields are derived from quantum simulations, and they can in fact do that. You go one scale more, and you come to molecular dynamics. In this case, the force fields do not have the capability to study reactive simulations, reactive dynamics, or chemical reactions, processes like that. But on the other hand, to describe mechanics in the system, these molecular dynamic simulations are sufficient, okay? So on the largest scale, we can go now to several billion atoms, okay? So I think we can approach system sizes on the scale of a micron, so micron cube.
If you're working with the electronic waveforms, these are single particle waveforms.
These are single particle waveforms.
How do you enforce Pauli symmetry?
So, it's time dependent density functional, okay? So that takes care of that, okay? So we have an effective exchange correlation potential. Okay, so now that's not the only thing. If we want to go to larger length scales, we have coupled molecular dynamics to finite element. In this case, okay, the connection between molecular dynamics and finite element is sort of seamless. So what we have is an MD region, which is shown over here, and then we have a handshake region where the transition takes place from MD to the finite element. And we have done these kinds of simulations in the past, and I will show you, for example, how we test this. I'm going to send a stress wave through the system, and you would see there are no reflections at the boundaries and so on. It seamlessly goes through the entire system. Okay. So let me go back. So you can see the stress wave going through the system, no reflections over there, as you can see, and it works fine. So this scheme is robust, okay? And then we can also do one more thing, which we have, in fact, to study, for example, stress corrosion cracking, okay? So chemical reactions because of stress corrosion. In that case, on the largest length scale, we have finite element. And inside finite element, adaptively, wherever we want, we can embed molecular dynamics, whether reactive or non-reactive. So that's no problem. And then inside molecular dynamics, okay, especially in the reactive part, if there is a need, we can embed quantum simulations. And that is also adaptive. So these three scales, okay, going all the way from electrons to continuum through, okay, mesoscale and everything, that can be done these days, okay? So these are our simulation capabilities. And let me just spend a couple of minutes, because I think yesterday I enjoyed Daniel's talk, and I thought I would mention some of the things we have done very similar, okay, to the experiments that he described, but on a smaller scale. So for example, our grains are in the nanometer scale, and this is a simulation we did 20 years ago, where we were looking at fracture in nanophase silicon nitride. So the system is made up of nanoparticles of silicon nitride, and we did exactly what Daniel was talking about. We sort of sintered the system first, okay, made a solid out of it, and then we studied fracture in that one, okay? And so on the right-hand side, what we are showing you is an atomistic view of this is the crack front, okay, the magenta, and the red colors are the damages in the system, like in the form of pores and so on. So this is in the past, and I thought, I would also mention in connection with the theme of the conference, we have looked at, things like cracks in glasses and so on, disordered systems. And we have looked at cracks both under compression, under tension, and so on. And this is a simulation we did, again, about a decade ago. And here we are looking at cracks under compression, and then what you see are wing cracks, okay, over here. So these are the wing cracks, and this is the damage in front of the system. And these are multi-million atom simulations, okay. And one of the earliest simulation, and at that time, I don't think the word graphene was known, okay, at least we didn't know it. And so this is 20 years ago, we did this simulation of fracture in a single sheet of graphite. And so this is a graphene simulation. I think this is the first simulation of fracture in graphene, okay. So this is in the past. So let me move okay, to the three things that I want to talk to you about. So first, plasticity and fracture in aluminum nitride. So aluminum nitride, as you know, is a hard material, okay, and it's a ceramic, very brittle. Now, our interest in this is we want to know when aluminum nitride is used as a coating, okay, what is the nature of damage? So for example, in satellites, okay, when meteors attack it, okay, or there are collisions, and these collisions can be very violent at the speed of 40 kilometers per second, okay? And so we wanted to study, okay, fracture in this at very high strain rates. So I will describe to you, so this is a simulation, 209 million atom, okay? I'm showing you a cross section of this, and there would be an impact damage in this one. And first I'll show you the movie, and then I describe to you, what is the kind of damage we observe. Okay, so there is impact, and you see this region, I will describe to you what it is. So stress waves are going, they're reflected from the boundary, come back, and then you would see a lot of damage in the form of nanovoids, cracks, dislocations in the system, and all of that, okay? So now let me describe to you what actually happens in the system. So the thing is, aluminum nitride, okay, crystal, it is in, when you start unstrained system, it is in the Woodside structure. So in the Woodside structure, if you look at an aluminum atom, so it has four-fold coordination. And under compression, when the pressure is more than 25 GPa, it undergoes a structural phase transformation, and the structure changes from this to rock salt structure. So rock salt structure is sodium chloride kind of structure, in which case an aluminum has 6 nearest neighbors, okay? So that's the transformation. So what you saw in the movie was the stress wave was going, it produced, okay, compression exceeding 25 GPa, and there was a structural transformation happening in the system as the stress wave was going. So what you're seeing over here is, this part, okay, over here, this is all rock salt. This part is Woodside, okay? So there's a structural transformation taking place in the system dynamically. And what happens then next is the stress wave will go and be reflected from the boundaries. And when it is reflected, then what happens is it comes to the boundary of the rock salt Woodside structure. So now at this structure, there is a lattice mismatch between the Woodside structure and the rock salt. And because of this lattice mismatch, there are strains at the boundary. The stress rays reflected, okay, from the back end of the sample comes, and when it hits this interface between rock salt and Woodside, it begins to nucleate defects. So the kind of defects we see over there are nanovoids, for example, over here, okay, at the boundary, and then these nanovoids grow, they coalesce, and then you begin to form cracks also, and this is happening at the interface of the structural phase transformation. In addition, what we see in the system are dislocation loops, and so these are the dislocation loops in the system, and these are dislocations running through the system, forming a sort of a kink band, okay? And so you have both kinds of cracks. You have cracks under tension, so that's mode 1, okay? And in addition, okay, you have these dislocations running through the system. There is also shear at the boundary of the Woodside rock salt structure, and you also have mode 2 kind of cracking in this system. So what we have then is a situation, okay, where we see 2 modes of cracking after some time has elapsed. And so we see these cracks, which are sort of mode 1, and you have mode 2 cracks also. So to summarize this part, okay, in this impact damage simulation on aluminum nitride, I think the key message is you see a structure phase transformation from Woodside to rock salt. At the Woodside rock salt interface, there is large lattice mismatch, and when the stress wave reflected from the back end of the sample hits this interface, that's where the damage begins. And the damage is in the form of, shear band, dislocation loops, nanovoids, crack, sort of very rich. Okay. So, in this system, okay, atoms which are not 6-fold coordinated, from there we do the analysis to find what the dislocations are. So in this system, the dislocations are not running straight like you see in crystals, okay? So they are these defects are in the form of loops, okay? So. Sorry?
It's analyzed in terms of Bourgain vectors.
Right.
So you need a lattice.
Right. Absolutely. So any other question before I move to the next part? Okay. All right. So let me come to the second part. So now I'm going to shift to metamaterials, and I will describe to you one of our simulations on high straight deformation. So now we are, looking at ultralight materials. The density of these materials is 0.9 milligrams per cc. Okay, so that's very low. Air density is 1.2 milligram per cc. So these are really very light structures, but very robust. So this is an experiment, okay? This is, I've taken this from this paper, and I will show you a movie, and you see, how flexible this architecture is. Okay, so this is a flat punch experiment, compression, okay. And then the punch is pulled out.
What is the scale?
Huh?
What is the scale?
Of the scale, I will describe to you. Okay, Nick? Okay. So these are, several microns, okay, scales. And if I'm not mistaken, this experiment was done at Caltech in Julia Greer's group. Okay, so this is these light cellular materials are made from nickel, and I'll describe to you the simulations we have done. So the basic building blocks, okay, what the experimentalists are using are sort of two kinds of lattices, and so they are made out of nickel tubes, okay, nanotubes, and these tubes can be hollow or solid, okay. So this is one kind of lattice, it's called Kagome lattice, okay, and this is the structure, and this is another kind of structure. So what we have done, we have looked at this structure and its mechanical response to uniaxial compression, okay. So the system we have is this, okay. So this is our structure, and we have used two kinds of nickel nanotubes. One are hollow and the other one solid, and that's the only difference between them, okay. And then so these things are sitting on a substrate, and then we do flat punch. So we push, okay, the punch. The speed is 2 meters per second, okay. Of course, our rates are much higher, okay. And that's our limitation, okay, in simulation. And so I will show you, okay, what happens to this system, okay. Okay. First, the stress strain response of the two systems. So this blue curve, okay, this is for a Kagome lattice made of solid nickel nanotubes. The red curve of nickel nanotubes which are hollow. So that's the only difference. And as you can see, the response of the hollow, okay, nickel lattice, nickel tubes is much better, okay? And you can see, you know, that the system can really sustain, okay, very large strains. And now I'll show you what is the mechanism and why it is happening. Okay. So this is a movie. I'll show you the deformation in flat punch and then how the system responds. So these things I will explain to you what these are. So this is one flat punch experiment, okay? And then I will describe to you the two kinds of lattices we have. Okay, so first the Kagome lattice of nickel nanotubes, okay, which are solid, okay? And in this case, I will show you, okay, in this movie. So dislocations are formed in the system, but the dislocations are coming, you know, from the flat punch and Kagome structure interface and also from the substrate. So the dislocations nucleate at the boundaries and then they travel to the midpoint, okay? So that's one. And now this is a Kagome lattice of hollow nickel nanotubes. Same thing, and the response is totally different.
So where the Kagome lattice?
Sorry?
Where the Kagome lattice? Kagome lattice.
So this is a sort of a cross section of the Kagome lattice, okay?
But I can't see any Kagome lattice on the.
The reason you're not seeing is because I'm just showing you a cross section of the thing, but it is a three-dimensional structure, okay? So
Kagome lattice on what scale? Because I mean, just
so the scale. So these things are, you know, like 70 to 100 nanometers in length, okay? Each one of these legs, okay? So each nanotube is between 70 to 100 nanometers. And then the structure is...
so the tubes are inside the bars of the X.
Exactly. So this is the actual structure, okay?
The lattice is inside that.
So this is the flat punch, and this is the substrate. So this Kagome lattice is resting on the substrate, okay? And then we are pushing this.
So just combination of some pillars that does not look like Kagome lattice. Kagome lattice is just dual lattice of honeycomb,
Right. So I'm just showing you a part of it, okay?
A part of it. So
Right.
that blocks arranged,
Right. Okay. So I'm just showing you a part of it because the thing is, I couldn't show you the entire movie. Okay, so coming back to this is in the hollow case, and here, okay, as you can see, the nucleations really start from here and then they travel in the system. So that's the difference between the nature of damage in the two systems. In this case, you know, dislocations are localized near the center of the system.
Sorry, what does the color coding mean, the dark red and the green?
So these are, you know, dislocations, okay?
You're tracking the Burgers vectors or something?
Correct. Okay. And then we did, you know, local deformation analysis on this, okay? So, and that is, of course, assessed by this parameter, okay, which Michael Falk, I think, introduced, okay? And it's a useful parameter. And then, you know, at a local level, we can study what the strain in the system is, okay, where, you know, for example, dislocations are forming and so on. So we have done this analysis on both kinds of systems, okay? And in this case, the local deformation analysis, you know, corroborates what I was telling earlier, that, you know, dislocations start from the flat punch and also from the substrate, and travel to the middle. And this is where most of the local deformation is. And then in this case, in the solid nanotubes, we also see other kinds of things. You know, we see slipped regions, okay, twins, for example, in the system, okay. And this is one snapshot at 12% strain. We have gone to much higher strain. You know, these systems can be strained to something like 20, 30%, and they respond beautifully, okay. So very robust structures. And one, you know, we find that one useful variable to describe deformation in this system, this is a very simple variable, is simply to look at angles, okay, between the beams in the two cases. So in the case of hollow lattice, you can see these angles are much smaller. In the case of solid lattice, the deformation is much more and the angles are much larger. Okay. So, so let me summarize this part. And so, you know, we looked at yielding in two kinds of system, one hollow nickel nanotube structure and the other one solid nanotubes. Okay, and the difference between the two is that beams deform before yielding, and we see slipped and twin regions in the structure with solid nickel nanotubes. And in the case of hollow nickel tubes, up to a strain of 11%, okay, we don't see any really deformation, okay, and then beam bending is observed after that, okay. So now what we are doing is, on these kinds of mechanical metamaterials, is we are looking, so we are very interested in layered materials. So we take layered materials like, you know, molysulfide, you know, molyselenide. So these are atomically thin layers, and so we take these thin layers and we are making origami structures out of them and then studying the mechanical response of those systems. So that's where, okay, this part of the work is going. Any questions before I move to the next part? Okay. So the last part is crack healing in ceramic nanocomposites, okay. And so simple, aluminum oxide crystal, okay, under stress, okay, uniaxial stress, okay, the crack goes through, it's a brittle material, okay, it's really not very useful for many structural applications, okay. But, you know, there were experiments done in Japan, and what they did was they embedded silicon carbide nanoparticles inside alumina, and they studied the response of this system, mechanical response, okay, to strains and so on. And so this was studied at sufficiently high temperature. So what happens there is that first silicon carbide oxidizes. So then you have a formation of an oxide layer on silicon carbide nanoparticles. And then, so this is the chemical reaction. And what they found is that this system, okay, when cracks are formed and so on, they're also healed in the system, okay. So when they do post-mortem on these systems, they find that the cracks have healed. And so we wanted to understand what is the mechanism of all that, okay. So as you can see, you know, there are several applications of these things. So the system we have simulated, so these are reactive simulations, so, you know, all bond breaking and so on are correctly described, okay. So what we have is, you know, alumina matrix. It is pre-cracked, and in front of that, you have a row of nanoparticles. So these nanoparticles are silicon carbide with an oxide layer. So silica layer on top of silicon carbide. Now the thing is, if we actually study silicon carbide oxidation, that's a very long time process, okay? We have done that, okay? But that takes a very long time. So what we did was, we took silicon carbide particles which were already oxidized and embedded them in this alumina matrix. So what you're seeing, so it's a core shell structure, the core is silicon carbide and the shell is silica. And we have studied this as a function, you know, we have several rows of this, 1 row, 2, 3, 4. We just wanted to see what happens, okay, to cracks in this system. Okay. And so the first thing is, first sort of crude observation is, so when we look at, crack healing in this system, we find, and it's sort of obvious, I mean, it's not surprising, that if the distance between nanoparticles is large, what we call large is if it is greater than 20 nanometers, okay, the system tends to fracture. Okay, alumina matrix, the cracks goes through, it fractures. However, if the interparticle distance is on the order of 20 nanometers or less, okay, then we see crack healing. Okay, and so this is what it is showing. So these samples were healed, these samples fractured. Okay. So the question is, what is the mechanism? So we examined several things. So one of the things we looked at is you have crack nanoparticle distance, and we wanted to see what is the effect on this separation, okay, of strain. So how does strain affect this? And we also looked at, the distance between nanoparticles and how that is affected by strain in the system. Okay, so we are applying strain from outside. Okay, and these simulations were done at 1700 degrees Kelvin because we wanted to be close to experiment. Okay, the experiment I described, which was done in Japan. Okay, so trying to be in the same ballpark, okay, as the experiment. Okay, and so from here you can see what happens is, even at a very small strain like 2%, okay, the separation between the crack and the nanoparticle decreases very rapidly. Okay. And that you can see. At the same time, the distance between nanoparticles is also shrinking, and so there is a coalescence of these nanoparticles. So I will describe to you these processes. So I'll first show you a movie. So what we have is, this is the pre-crack in the system. Okay, this is a row of nanoparticles. I'm just showing you one nanoparticle in this case, but there is a row. Okay, and so this one, red and yellow over here, these are silica, and inside what you see, that's silicon carbide. Okay, that's where the healing will begin. So I will run the movie, and then you can see what's going on. Okay, so as you can see, okay, both are approaching each other, and then you can see silica flowing into the crack in alumina, and the nanoparticle stops the crack growth. Over here, I'm plotting, okay, the self-diffusion coefficient of silica, okay, so silicon and oxygen both, as a function of strain. Okay, so what we see is, up to 2%, I showed you, okay, that the distance between the nanoparticle and the crack was not much affected, but after the strain exceeds 2%, okay, the self-diffusion coefficient for silicon and oxygen jumps, okay, and then you can see a rapid increase in it. And this is the cause of healing of crack in alumina. So silica is in fact diffusing into the crack and repairing the crack. Okay. So, and then we can calculate stresses in front of the stresses between the crack and the nanoparticle, and what they are doing to diffusion of silicon and oxygen. Okay. So the message here is, it's really silicon and oxygen diffusion into the crack that is stopping it. And so again, we did local deformation analysis, and this sort of picture shows that this is the pristine alumina matrix, and over the damage is sort of in this region. Okay. So this is the local deformation analysis, and this is the damage part. Now, what we found was certain things change in the damage zone, but not a whole lot. So one of the things that changes is this aluminum, oxygen, aluminum. Okay, if you look at this bond angle, okay, so aluminum, oxygen bond, and then you pick another aluminum. So this angle, this is the one where we see major changes. So as far as the lattice is concerned, okay, in the damage zone, okay, that's where sort of bond angles are changing. If we go more into the system, what we find is this is the alumina matrix, which is unaffected. Okay, so here not much change has happened. The damage is accumulated over here. So over here, you can see, okay, there is, there is one grain over here, okay? Crack has not gone through here, okay? So there's one grain over here, one grain over here, and this is sort of the grain boundary, okay? So from this system, okay, nanoparticles which are repairing the crack through the flow of silica, the additional things we see is one, these silicon carbide nanoparticles, they rotate, okay? And when they rotate, we see the formation of these grains, okay? So there are grain boundaries in this system. And in addition, what we see is we started with a spherical nanoparticle, and then there is a phase transformation where you begin to see faceting of these nanoparticles. So these are facets, okay, in the system. And this is where the silica is flowing into the crack and stopping it. So this is a snapshot at one strain. If you keep increasing the strain, you begin to see, how this damage zone grows, but still no cracks over here. And then you have, this grain growth and grain boundary formation. Now, at these, if you keep increasing the strain at these boundaries, in the grain boundaries, you can begin to nucleate cracks. And what we find is that when that happens, okay, silica flows into those cracks also, these secondary cracks, and repairs them also, okay. And so we have done this as a function of, several particles, gone to very large strains and so on, okay, studied, the nature of damage in these systems. And so the summary of this thing is that crack healing does indeed occur in alumina when you embed it with silicon carbide particles as the core and silica as the shell. And silica is really mainly responsible for healing the cracks, okay? And in addition to the healing, what you see is nanoparticle rotation, grain growth, and grain sliding in the system, okay? So these are the three simulations I wanted to describe to you. And let me end my talk, okay, by showing, first let me show you this and then I'll tell you, okay, something that is we find very interesting, okay. So this is a simulation in which we have silicon carbide fibers embedded in silicon nitride. And so you can actually, the nice thing about these simulations is you can actually go and you can actually go inside your simulation and look at fracture surfaces. So now this is a simulation where we can actually go inside, okay, the fracture surface and examine it. So on the screen it is not as sort of impressive, but we have this three-dimensional visualization. So there we can actually walk into this fracture surface and we are totally immersed in it, okay. And this is a huge, okay, visualization facility we have in our lab. So let me end my talk by telling you we are very excited about a new project we have started. So we have a center at USC. It is called the Materials Genome Center. It is funded by the Department of Energy. And Department of Energy funded only 3 centers in the country. And one center went to Argonne National Lab, the other one went to Brookhaven National Lab. And they gave only one center to a university of all the universities in the US, and we are very fortunate to have that, okay. So in this, okay, we are looking at layered materials, and I'll tell you what we are doing. Okay, so let me give you the background of this project. So President Obama has been very supportive of science in the US, okay. I don't know what's going to happen next, okay. God forbid. So in the White House, there was an initiative, okay, to design new materials taking cues from biology, okay. Now, whether that is going to happen or not, that's not the point. But the thing is, this stuff sells. If you attach biology to material science, it sells, okay. So this is a very good packaging, okay, of material science. And so this report came out of the White House, and President Obama announced this initiative. Okay, so this is the science advisor of President Obama who sort of came up with this booklet. In this whole booklet, there was only one science picture, and we were totally surprised that this picture is from one of our simulations. So we were thrilled. So we started to count money when we saw that picture, as you can imagine. Okay. So then the Materials Genome Center happened, and so our team, okay, it's a very good team. So these are my colleagues, Priya Vishishta and Aichiro Nakano, okay? And so we have worked together throughout our lives, okay? And then there are two other people from USC. And so this is Oleg Presto. Oleg Presto does very beautiful quantum mechanical simulations. And Malancha, okay, is an experimentalist, and she works in polymers. And our idea is to take functional layered materials and functionalize them with polymers, and then make architectures out of them, okay? And on the experimental side, we have these two people, Uwe Bergman and David Fritz, and they do experiments at Stanford on with X-ray laser, okay, so free electron laser. And then we have David Singh. David Singh is going to look at thermal transport in these architectures, layered material architectures. Kristen, I mean, she is a specialist in high-performance computing and software dissemination, because our idea is to design software and disseminate it. Bill Goddard, you may know, okay, he's at Caltech. He's a computational chemist, and we have had long-standing collaboration with him. And then this Ajay is one of the finest synthesis person in the world, okay? He can, make materials unbelievable. I mean, he's very, very good. And so this is our team. And what we are looking at are, we want to design synthesis software, because our friends who do synthesis, they would like to have some sort of a software which has some predictive capability, okay? And so that's the main theme. And then the materials we have chosen are layered materials, okay? And we would design software for these layered material architectures, not just two-dimension, but three-dimensional architectures out of these materials. And we would look at electrical, optical, and so on. And we would provide software for the community for these kinds of things. To validate this software, we will do experiments at Stanford on the free electron laser and the electron diffraction facilities. So these are absolutely world-class facilities. And final goal is we would disseminate our software to the community. And so, the kinds of things we are working on now is exfoliation, because this is the primary method of making layered materials. And so we are doing simulations, okay, for exfoliation of layered materials, okay. So that's the synthesis part. And then this is functionalization part, and this is done by initiated CVD growth, and that's what Malancha Gupta does. And we would do simulations, not just to see how systems are functionalized, but also how the properties change with functionalization. And so, the whole goal is, the holy grail of material science, function, property, structure, relationship. That's what we are looking at, right? So there are interesting quantum simulation questions like, what are the non-equilibrium atomistic processes, electronic processes far from equilibrium? How do we relate our simulations to sort of pump-probe kind of experiments at Stanford? And I'm really intrigued by this area, and I think it has not been explored in material science, but I feel there is some potential in it. When you're designing these layered material architectures, okay, we find there is a lot of similarity with some of the things that have been studied in linguistics, natural languages. So we are trying to learn, to bring things from computational linguistics into the design of these architectures, okay? So that's an area, a new area for us, And of course that is related to data analytics. Okay, so that's our center. Okay, so let me end by acknowledging, okay, Priya, Vashishta, Ichiro, Nakano, they are my lifelong amigos, okay, so we have worked very well together. Paolo, came and worked with us as a student, and then he went away and worked with David Strolowitz, and now we are bringing him back as a faculty at USC, so he's going to join in 2 days, okay, when the university opens. Pankaj Rajak is a senior graduate student. He's from IIT Kharagpur here. He's extremely bright, okay? And I'm telling you, that guy is an absolute gem. So he's doing his PhD in material science along with a master's degree in computer science, specializing in high performance computing and simulation. I think, Bonnie, you did probably the same thing, right? Right. So, this is something students in our group have done, and so they really know computer science very well. Okay, and Kenichi Nomura, he was a former student of mine, and he went into finance. Okay, now he's not so interested in finance, and he's coming back, so he'll be with us again. So, and the research is supported by DOE, NSF, Air Force Office of Scientific Research, and Army Research Lab. So with that, okay, thank you very much for your attention.
Thank you. So, question, comments?
This was regarding the metamaterial modeling. So you showed atomistic simulations, right? And have you tried to match with this FEM kind of modeling? So are there attempts to do more meso modeling or continuum modeling for this metamaterials and to go across the length scales?
Right. So we haven't done it, but we have planned these simulations. Okay, because with MD and finite element, because they can be joined very well. So I think it should be possible to sort of do that. So in fact, we will not require any coarse graining of the MD. We would straight do MD and finite element joined together.
Because you showed us only one unique cell, right? The one cell of the metamaterial.
No, I showed you a part of the system. So this is a billion atom simulation. Okay, because just for visualization purposes, I just showed you a part of the system. I think that was your question also, but it is actually the whole structure. But your point is well taken, because the thing is, what we are studying, we are still limited by time scale. Okay, so your point is well taken. If we want to go to longer time scales, we have to bring some of the description from the continuum. Okay, so.
Yeah, I mean, this is sort of amazing because, here you're focusing on materials, but you could also zoom back a bit. You could also zoom back a bit and use it to answer basic unanswered physics questions, maybe.
Right.
General principles of crystal growth, that
Right.
is how and then how to optimize crystals and so on.
Right.
And things like shape memory materials, iron, palladium, nickel,
Absolutely.
titanium, and when you cycle it, where does the memory go? Is it
Right.
multi-scale and so on? Are people looking at this?
Wonderful, beautiful questions, okay? And some people are looking at it. One person I know, okay, who is sort of very close to us, and which is Kaushik. Kaushik has been looking at shape memory systems, okay?
No, Kaushik Bhattacharya.
Kaushik Bhattacharya.
So is he using your center? The simulations are
No,
done.
he's not part of our center, but we do collaborate with him,
Okay.
okay? And he's very interested in atomistic simulations as well, okay? And so I don't know, what is the latest status, okay, of his work, okay? But I know I've talked to him often that he is very interested in shape memory systems.
And in the present context, you could do this in any geometry, including a spherical shell of silicon dioxide with irregular plates on it.
Absolutely. Okay, I'm telling you, the way computing is these days, it is so good, okay, that you just dream the kind of simulation you want to do, and I think it is possible, okay, and things are only becoming better.
shown how it is possible to cross the length scale by completing from continuum mechanics to finite element. Are there similar tricks to go across time scale and to go to simulate stress corrosion or even aging or plastic dynamics? And
So,
from calculus long to
so the thing is, stress corrosion cracking. We had a center on stress corrosion cracking, okay? And so this was Caltech USC, okay? And Michael Ortiz, Bill Goddard, and these people were involved with us. So as you know, Michael Ortiz, his interest is in the continuum and, you know, longer time scales and so on. So we have looked at stress corrosion cracking. In particular, how, for example, you know, water reacts with silica. Okay, and so we have looked at, we have also looked at, you know, metallic systems, okay, for example, embrittlement of metals, okay, by things like sulfur and so on. So we did look at that. Now the thing is, as far as time is concerned, okay, so these days with MD simulations, multi-million atoms, you can go to microseconds, okay. So, you know, the longest simulation we have done in our group is 15 microseconds. In our group, we have done fracture simulation. So the 15 microsecond is a biological simulation. Fracture simulation with multi-million atoms, we have gone to 1 microsecond. So as, you know, I was mentioning to you in our private conversation, so the thing is, now when you are at microsecond, we are 2 or 3 orders of magnitude away from high strain rate dynamic measurements, for example, the kind Ravichandran does. So that's the gap. Now, we can do something better. If you say there is a rare event in the system, and I want to study a rare event in the system, then there are approaches, simulation approaches, with which we can go much longer. So one such approach is metadynamics, okay, which Michele Parinello developed. So, you know, one can use that for rare events. And then there are other, approaches. So it's very simple. What you need to do is, you know, things slow down when you have to cross very high barriers. So if you just find out what the energy barrier is, then you know what the time scale is, roughly speaking. And then you can start using these accelerated approaches to overcome these barriers and explore the phase space, okay, much more readily. So it is possible. But if you say do a straight simulation for a millisecond, that's not possible unless you have a special machine. And the only person I know who has a special machine is David Shaw, okay, who made a killing in the, you know, in finance, made billions of dollars, and then retired and decided to do biophysics, right? So he has a group of 100 people. He has his own machine which does electrostatics. Okay, it's hardwired. So Coulomb interaction is hardwired, and he can reach milliseconds. So he's studying protein structure. He, you know, his thinking is, I've made enough money, let me now win a Nobel Prize. Okay, so, but we don't have these capabilities. So you really need a special machine for that. So.
In the second part, you talked about very light material.
Right.
So that lightness plays a significant role in your, so that material is very light. But what is the, specialty about that light material?
So the thing is, you know, if you talk to people in aerospace industry and so on, they're always looking for very light materials, but okay, they want these materials to have fantastic mechanical response also. Okay, so that's the interest. Okay, from the applications point of view, and so you know, a lot of these nanoporous systems. Okay, where you can go to very low densities. Even silica gels, for example, you can go to extremely low densities, and so they are very useful when you're making composites, for example. Okay, so.
So basically, so application, interesting.
It is application.
So from fundamental physical science, its lightness.
So yeah. So there are some really very interesting fundamental questions. One of the very interesting questions is, if you have if you have a fluid in these structures, nanoporous structures, so let's say water, okay? What is the behavior of water in these, nanopores, okay? And apparently there are exact predictions, okay, by mathematicians saying that the dynamics of fluids in these nanoporous system would show you stretched exponential behavior with an exponent of d divided by d plus 2, where d is the dimensionality of the system. And this is if you don't have long range interaction. If you have long range interaction, it becomes d star divided by d star plus 2. So there are fundamental predictions by mathematicians, totally robust, and you can actually go and check by simulations, and we have done that, okay? So the behavior of water, behavior of fluids in these nanopores, that's very interesting. So
It's not aerosol, real material. It's crystalline.
right, basic structure comes from crystalline, but there are a lot of, open spaces in these materials. So.
So any other questions, comments? Yeah, please.
So what is so how crucial is the quality of the potential?
Very good. So these days, the quality of potentials is very good, okay, depending upon what questions you ask. That's always the case, okay. So all of these potentials have been derived on the basis of quantum mechanical calculations and validated by experiments, including electronic excitations in the system, okay. So, far from equilibrium processes on very short time scales that can be probed experimentally, pump probe experiments, and we can compare them, right? And so these simulations are reliable over there. And then, there are other processes in the system, okay, bond breaking and so on, okay, and those descriptions are very good also, okay. Now, if you say, does it work for everything? The answer is obviously no, okay. So you have to first decide, these are the questions I'm going to investigate. So you formulate the questions first, you design the interaction that would at least address those questions properly, okay. But one of the main problems with these potential is always transferability. They are not transferable to every situation.
Reactive, so I guess they are some
Right.
dependent on the time.
Right. For example, a few years ago, you couldn't study structural phase transformation unless the force fields would change as the atoms moved, right? Because the neighbors change, so, you need a complete description of that. Now we can do that. No problem.
Any other? No. If not,